In this session, we're going to talk about combinational logic design, which consists of two parts. The first part will be dealing with the implementation technology and logic design part, and let's start with this one. The first part will be dealing with the design procedure, where it consists of the specification, formulation, optimization, and technology mapping parts. Then we will talk about the hierarchical design, and then we will go in detail about the technology mapping, where we talk about NAND NOR mapping, and finally we will conclude with the verification, where we have manual or simulation approach for circuit verification. The second part will be covered in the next session. And we should keep in mind that the combinational circuit has a set of m Boolean inputs and has n Boolean outputs. It matches them with n switching functions, where, because you need a switching function for each of the outputs, that's why we have n switching functions, and we can have 2 to the power m input combinations here. Each of them should be matched with an output here. This is what we call a combinational logic, basically. The design procedure starts with the specification, what customer requests or what your teacher asks from you. So you write the specification for the circuit if one is not already available, if one is not already given in detail. Maybe it can be blur, especially if usually the questions will have the specification, the exam questions will have the specification, but customers may have some blur ideas about the product or about the service that they ask from you, so you need to help them specify it as well. So specification part is very important. Maybe you can remember that, like the solving a question means. So understand the question first. I mean, you first need to understand the requirements here. So this is about the specification part. It should be perfect, of course. Otherwise, you will be designing something irrelevant. Then comes the formulation part, where you derive a truth table or initial Boolean equations that define the required relationships between the inputs and outputs that we mentioned in the previous slide. Again, maybe they are given in the specification as well. Most probably in an exam question or something, it is possible. But usually, if you're dealing with customer requirements, I mean, you need to do this. You need to formulate it. Then you apply hierarchical design here if appropriate. If it is required, you take that step right here. And you go ahead and do the optimization in the third part, where you apply two-level and multiple-level optimization here, and you draw a logic diagram or provide a netlist for the resulting circuit using the basic gates at this moment, like the AND, ORs, and inverters that we know from our previous sessions. Then we go ahead and do the technology mapping, if it is required, where we map the logic diagram to the implementation technology selected. Maybe we will be asked to map it to NAND gates or NOR gates. It depends on the question. And the final part is the verification part. This is usually done in laboratory works or real products. I mean, usually in the exams, you verify them for yourself, or your teacher or the one who grades the exams will do the verification, of course, in case of how you solve the problem. So you verify the correctness of the final design here. It can be either done manually or using computer-aided tools with simulations. Every step will be explained in the textbook with an example, with a design example here. What we're trying to do here is, the first part will be dealing with the question. We're trying to implement a BCD to XS3 converter. This is all you have, okay? Suppose that this is the only sentence you have in the question. Just design a BCD to access-tree converter and show the steps, whatever. So what we're trying to do here is access-tree converter just adds 3 to binary coded decimals here. It means that we will have a set of 10 inputs and they will be matched with 10 outputs, symbols, okay? 10 input symbols to 10 output symbols. But in binary system, how can we represent them? These 10 symbols with 4 bits and 4 bits again. So binary coded decimals will be covering 4 inputs, 4 bits for 10 symbols, and you will have 4 outputs as well, again, for 10 symbols. So the implementation part will be dealing with a multiple level circuit, and we will map the circuit in the final design to NAND gates. Let's see the steps one by one. Now we go ahead and do the formulation. You have here all 10 input combinations here, all 10 symbols here, and these are your 10 outputs, and the relationship between them is just adding 3. Okay, what happened to the symbols or input combinations that 10 or more up to 15, what happened to them? They're X. Okay, those input combinations will never occur, so we will consider them as X's. That's why we didn't put them here in our truth table. In the exam, you can put them in detail. It would help the grader to understand. So let's go ahead and transform these truth tables into those K-maps, okay? What we're trying to do here is drawing a K-map for each of the output variables. Okay, for this one, you need to have another one. For this one, you need to have another one. And for Z, finally, you need to have another one. And you put them in their correct locations. Suppose that we're dealing with W, for example, you will put 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, okay? 5 zeros and 5 ones sequentially. So what you have here is 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. Then the remaining ones are what? X's. X, 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 X. That's how we fill all the truth tables. So we will have a truth table for W, Y, X, and Z outputs in the end. We have all of them transformed here. And you should remember that this is already labeled for us. You see, it has the labels. But this is how we make the positioning. Okay, A, B, C, D are located like this in our truth tables. Now we do some optimization. What was K-map optimization? We're trying to get the largest possible rectangles here in the size of powers of 2. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4 is our maximum number of inputs. So our rectangle sizes will be 1, 2, 4, 8, or 16. That's it. That's all we can have here. Let's do them step by step as given here. Pause the video here and do them yourself, okay? And compare your results with the optimizations given here and check if you're doing it perfectly okay or not, okay? Just pause the video and do them on your own now. Okay, the largest possible one is this one, which is basically A. And the next one is this one. It is obvious that it is BC, this one. And the next one is this one, which is DC. Oops, no, BD. Okay, this one. So W is all right. That's done. And what about X? The largest possible. This one is what? It is DB naught. This one is DB naught. And the next one is what? This one, right? So what is this? It is CB naught again. So this one is this one. And finally, you will have this one. What is this? It is B C naught D naught. Okay, this one is this one. Great. And then we're done with X as well. Let's move forward to Y. It's pretty straightforward. This one is what? It is C0, D0. And what about this one? It is CD. And this one is CD. It's pretty obvious. Okay, so we're done here as well. And finally, the last one, I think that this is the easiest one, right? So this one is D0 directly. So what we put here, all right. So we're done with two-level optimization here. But are we finished? Just pause the video and think about it. Are we finished here? No. We can go ahead and go for multiple level transformations that we discussed in the previous session. These are our original output equations here. And what are the costs here? Okay, it's 2, 2, 3, 7. It is 2, 2, 3. Combined to a 3-input gate, it is 10. So, and how about this one? It is 2, 2 connected to a 2-input OR gate, it's 6. And this one is a direct cable, right? Okay, you have an inverter, but it is given here in gate cost. That's it. So you don't count the inverters here. So the total cost here is 23. Now, if we perform extraction here, like we find the common term here, is it possible? Yes, it's pretty obvious. I can see some, let's say, combinations possible here, like B, C plus D here for this one. And again, for this one, it is B not C plus D. I can write it like this, right? So I say that your CD is, I will use them as common factor here, CD, and write them as T1, T1. So it will give me a different cost now, okay? What would be this cost? Let's calculate. So you need to have an extra output, or let's say middle output, where you have it in the middle layer. I mean, it's not in the customer outputs, but it is a pre-output in our design. So it would cost us 2. Here it is. And the next one is like a 2-input one into a 2-input one. It is 4. And a 2-input one, 3-input one to 2-input one, 2, 3, 7. It is 2, 3 is 5, then 2 is 7. And then this one is 2, 2, 2. It is 6, and this one is again direct cable, so it is 0. So what you have here, the total output will be 19. So as you see, when we perform multiple level optimization, it has been dropped to 19 here. Can we do more here? Is there anything we can do with what we learned so far? Can we do anything more here? Just pause the video and think about it. Yes, we can go ahead and do a bit more here. Look at the beautiful thing here. Like, what is this? By De Morgan's law, right? I'm sorry, this one is, of course, and. Okay, so it means that this one is your T1 nut, and this one is your T1 nut again. See, this is beautiful. This is absolutely beautiful. Now let's take a look at the cost. So as you see, it is 2 into 2, it is 4. And the cost of this T1 CD is solid here, it's 2, right here. And this one is 2, 2, 2, it is 6. And this is 2, 2, it is 4, this one. And the resultant circuit cost is 16 as gate input cost. Okay, so it is much better if we take this extra step as well. And what about the gate input cost of with nuts here? If we calculate them as well, just for exercise here, like you say, an inverter here, an inverter here, an inverter here, your GN would be 19 here. And what would be your GN here? For example, here it would be in the upside, it's with 1, 2, 3 again. So it would be your gate input cost with nuts will be here 22. And what about the gate input cost with nuts here in the original function here? It would be B, D, and C inverted here. That's it. And it would be 26. That's all about the optimization part. The thing is, we first apply straightforward two-level optimization with the K-maps. Then we use our experience and creativity to come up with some better, less cost, multiple level optimized circuit. That's the idea, okay? That's the idea with optimization, and that's what you're going to be asked for in the exams. Okay, now the next step is the technology mapping part. We're trying to map our circuit to a standard gate, to a universal gate. To a universal gate. Either it can be a NAND or NOR gate. Here in this question, we're going to map our circuit to NAND gates. Okay, there will be all NAND gates. This is also a NAND gate implementation. The NAND and NOR gates. That's it. And we will use only NAND gates here in this matter. We will see this. And let's take a look, say a few words about the hierarchical design. Why we're doing this? We're trying to control the complexity of the function where you try to map the inputs to outputs. Here, what we do here is decomposing the function into smaller pieces called blocks. Okay, like they're Lego parts that you can use for other parts of the you can use in other parts of the circuit as well. So if you have a meaningful functional block, you can go ahead and decompose that block into blocks as well. Okay, so until all the blocks are small enough, I mean you cannot decompose them anymore, it means that you're done, and they are called a primitive block. So the collection of all blocks, including the decomposed ones, is called the hierarchy. For example, what we're trying to implement here as an example will be a 9-input parity tree. And when we look at this in top level, like from above the forest with a drone or something, we will see some functional blocks as trees, right? It's like looking at the top level, and you will understand that it should be a box where you have 9 inputs, 4, 5, 6, 7, 8, 9, where you have one. I'm trying to design this box, right? And within this box there will be smaller boxes, and within those boxes there will be smaller boxes, or also blocks. That's it. And here, how can I divide this? We will have 4 3-bit even parity trees in 2 levels, we will see, and within those blocks we will have 2-bit exclusive OR functions, and that's it. And they will be implemented with the NAND gates only, and the total design will require 32 2-input NAND gates. How can this be possible? Let's take a look at this. It's pretty easy. This is what you're being asked. If you formulate this in a Boolean equation or something, it would look rather complex, okay? But if you apply hierarchical design here by using functional blocks, it would be piece of cake. It would be very easy. Look at our approach here. A 3-input odd function here to get the even parity. You need to have odd function. We discussed this in the previous slides, previous sessions. Another one and another one for each set of 3 inputs here, right here, okay? See? They're divided into T. And then the resultant ones will be fed in another 3-input odd function as well, and the resultant output will be your even parity output. Okay, that's it. And are we done yet? No. And what about what is in those blocks? in those blocks, each block, we have an XOR gate, okay, connected to another, this output, another XOR gate. So this is a basic 3-input odd function circuit where you have here, and for each of this XOR gate, okay, we haven't seen this yet, but this is the implementation of a single XOR gate by NAND gates only, and within each this box you will have this one. So in the end, these are in those, and these are put in those places, and what you have here as a total will be this box where you implement your problem here in a very, very efficient and practical way. So I hope you understand the main idea behind the hierarchical design. So whenever possible, we try to decompose a complex design into common reusable function blocks. And these blocks should be verified and well documented and placed in libraries for future use. I think you do this when you write software, right? Like maybe you have your already available some login procedures, some basic data structures, some functional blocks. You keep them for yourself, right? In your libraries or something, and you use them again and again. No need to write them again and again. So you maybe change a few variable names and just a few numbers, and you go ahead and use them. This is what we're talking about. The same thing here in hardware design. It's pretty similar, I guess. As we mentioned a few moments ago, a top-down design proceeds from an abstract high-level specification to a more and more detailed design by decomposition and successive refinement of those functions. Okay, what we do so far. A bottom-up design is reverse, just reverse. It starts with the basic blocks, primitive blocks, then you're going up by combining them together. It's a bit harder to see, and most of the questions and approaches used in the textbook, and I also myself use top-down approach usually in the problems. So now let's go ahead and talk about the technology mapping. So the mapping procedures cover mapping to NAND gates or NOR gates. Let's see how these are implemented. It's pretty straightforward. Now we assume that gate loads and delays are ignored. Okay, this is just an assumption, and this and the mapping is accomplished by whenever you see an AND or gate, you replace them with their NAND or NOR counterparts. And when you just encounter a inverter and a circuit like this, you push them in their fan-out points right here, fan-out points. You just transform this into all of them, like spreading the effect. And whenever you see a structure like this, after conversion, after mapping, you cancel those inverter pairs here. That's what you do here during mapping. Okay, how we do NAND mapping here? Whenever you see an AND gate, you replace it with an AND gate and an inverter. You see, it's pretty obvious. But there is another version of this, okay, like this is a B naught. It is A naught plus B naught, right? So it's the same. So it can have also the other structure like this as well. Just keep in mind. And whenever you see an OR gate, and you will just implement this with inverter pairs and an AND gate. So what should it be? N naught plus, A naught times B naught naught. So what should it be when you do the operation? A plus B, right? So the original one. That's why you implement them like this. is pretty straightforward. So whenever we see this, we will replace it with this one. Whenever we see this OR, we will replace it with invert NAND. Whenever we see AND, we will replace with. So look at the matching here. If it is AND, so you put the NAND first. If it is OR, you put the inverters first. Maybe you can remember, it's easier to remember. But don't worry, no need to memorize. You will remember them much better when you solve some examples on your own. So when you see a structure like this, you will just cancel. When you see a structure like this, you will just iterate or push the inverters from the fan-out points right here, okay? From the fan-out point, you send those inverters in their corresponding places. Now let's see how it goes. So this is our circuit that should be mapped to NAND gates. And what we do here is replace this one with NAND invert right here. Replace this one with NAND invert right here. Replace this AND gate with NAND invert right here. And replace this one with what? This is an OR gate. Invert NAND. And right here. Okay. So in the end, we will have this circuit now for canceling some pairs where required. Now let's do this. Be careful about the fan-out points here, right here, okay? This fan-out point here. What we do here is just iterate our inverters here in this fashion, okay? So this one will be gone, and it would be pushed from the fan-out point, and that's it. So what happens will be this one will cancel this one will cancel this one will cancel this one will cancel this one. You see, now what I have here as an inverter is just this one will be remaining and just this one will be remaining here. So that's the idea, and only this one will be remaining here, only this one will be remaining here, and the resultant circuit will look like this. Lovely, see? And maybe you can ask, what about the inverters here? Aren't we going to convert them? Yes, if you want, you can. And those inverters also correspond to, if you remember, if you connect the same output to an AND gate, it just inverts it, right? If you remember from our previous sessions. So you can also just change them to NAND gates as well. But in the exam, I don't want you to do it, okay? No need. I mean, if you do it, it's correct, but no need to do it because it's pretty straightforward. Now, mapping to NOR gates is pretty similar. Again, we make the same assumptions, and this time we're doing the trick like this, okay? Whenever you see an OR gate, you put NOR gate and put an inverter. See the matching here. Whenever you see an AND gate, you first invert the inputs and then put an OR gate. That's it. The remaining ones are exactly the same that we do in the NAND mapping part as well. We cancel them and we use the fan-out points to push the inverters. That's it. The other parts are the same. Now let's take a look at how it is done in our example for NOR mapping. This is your original circuit, and this one should be replaced with what? Just pause the video and do it on your own if you like. It would be invert NOR. Okay, this one. And again, this should be what? Invert NOR. This one. And this should be what? Invert NOR. This one. And this should be what? NOR invert, right? This one. So we put them in their correct locations like this. And in the end, we have this. Let's look at what we can cancel here. What we can cancel. Look at this. Okay. This one is a crucial one. Look at this particular fan-out point here. See? the fan out point here is this part. Okay, we iterate this inverter to here, and this will be gone, and of course these will be gone and these will be gone. Great, so good. But how about this one? Be careful, it will not be gone because there is no connection to this one, right? So C inverter will remain intact. Be careful. Okay, we're talking about this line here, and the inverter pairs will be gone here, but this one will be staying. Okay, this one will be staying here, right here. And how about this one? This is pretty obvious, they will be gone. And what else? Nothing. Okay, so we will keep this basic input inverters here, right? And we will keep the inverter of C here, right here, and we will keep the inverter at the out here, like this. So in the end, your resultant circuit will be this one, and it is mapped to NOR. Again, if you want to convert the inverters as well, so the inverter will be a NOR gate with the same input, right? So it can also be converted to an OR gate as well. The last part is the verification part. It shows that the final circuit designed implements the original specification, what you've been asked for in the question. Simple specifications are the truth tables, Boolean equations, or your HDL code. For example, you might have written your code in hardware definition language or something. You can also check this as well. If the above result from formulation and are not the original specification, it's critical that the formulation process should be flawless. If you're not, doing this, from formulation rather than input-output matching here, it should be flawless. That's what we're being told here. Because, if you have the input-output matching truth table, for example, it's pretty straightforward. But if you have a formulation as specification here, you should be careful. It should be flawless. That's what it tells us. Now, the basic verification methods are, the first one is, we mentioned maybe a bit, manual logic analysis. We have the truth table or Boolean equation of the final circuit here, and we compare the final circuit truth table with the specified truth table. We match them, or we can prove that the Boolean equations for the final circuit are equal to the specified Boolean equations. Either of them is alright. Or you can go ahead and do simulation. You can simulate the final circuit from HDL, for example. You can give all the possible input combinations for test, and that's it. And you generate all the possible test cases for all possible care input combinations from the specification. Do you need any test for the don't-care inputs? No need, because they will not be used, or those outputs will not matter to you anyway. So you go ahead and do the test input cases for all the care input combinations. For example, for our BCD to XS3 code converter that we discussed a few moments before, we go ahead and find the Boolean equations here, and we have the truth table from the equations, like this one. It has been given us in the specification, and you have another set of truth table for those Boolean equations too. Okay, if they match perfectly 100% over each other, it means that what you did was correct. So you test all the input combinations here. That's the idea. And the simulation procedure uses a schematic editor, like we were using Max Plus of Altera before. I think they switched to Quartus, I'm not sure. Or you can use any type of maybe Verilog or I don't know, model sim maybe. You can use a waveform editor here or text editor to enter a test combination consisting of a sequence of all the input combinations to be applied to the circuit. So this also guarantees that your circuit is done correctly if it is giving related outputs to all of the possible input combinations here. Again, you did this, all of these for only the care input combinations. That's it. However, yes, that test, even if you limit this with all the input care combinations, it can be time consuming or a daunting task. Why? Because when your input combination, when the number of your inputs, size of your input set gets larger, suppose that you have 100 inputs or let's say 1,000 inputs or something, as you see, when you the possible input combinations coming will be in the powers, right? I don't know whether you took complexity or something like this, but where you here you will face combinatoric explosion here. Like you need to, even with the computer, it can be a daunting task to test all the possible input combinations here. What you can do here, you can go ahead and study on maybe some efficient testing procedures or methods here, which rely on or get help from self-computing solutions or suboptimum solutions, suboptimum tests, or whatever maybe. Here you have a verification example using simulation. You have your circuit here mapped to NAND gates, and this is a complex gate, right? You remember it's AOI, which is your, what is AOI here? It is AOI, like and or invert like two input and connected to two input two like this one. Yeah, invert, I'm sorry, this is the invert. That's it, no need for this one. See, and this is the inverter here. And then you can enter a waveform that applies all possible input care input combinations here for this particular circuit here, NAND map circuit, and you check out the outputs here and check if are all BCD input combinations present. Okay, and then you go ahead and check their corresponding outputs in the given truth table, for example, in step 2. And then you can say that, okay, this circuit works or a problem. See, right here, give all of them and check them with the corresponding outputs here. Do they match? Yes. If yes, all right, you can go ahead and finish your design. Okay, this is all about the first part of combinational logic design, and thanks for